Hello and welcome to another lesson on GCSE physics. Today's learning intention is to know how mains electricity works. Now for the Do It Now task, which is a recap of previous lessons, I've presented for you here a parallel circuit which has got in it 3 loops with a resistor in each one. I would like to work out the values on the 3 voltmeters V1, V2, V3, the current A1, A2 and A3, and then the value of resistor R. Pause the video and have a go at working out the values of each of those, please. Okay, so let's have a go at looking at the answers to this circuit then. Just to aid my explanation, I'm going to get the laser pointer out so that I can show you the direction in which the current goes. Now, current will be leaving the battery, and when it does so, it leaves it carrying 12 volts of potential difference. Now, any of the current that goes this way will pass through one resistor, and it will give all 12 volts that it carries to that resistor, and so therefore the value of V1 is going to be 12 volts. Now, similarly, any current that goes through the second loop instead, as shown by the cursor here, again, because it only passes through the one resistor, it has to give all 12 volts that it is carrying to V2, and so the value of V2 is 12 volts, because remember that when the current returns to the battery, it needs to have 0 volts left. Then finally, and I'm sure you can see where the pattern is going now, when the current leaves here, if it doesn't go through that loop or the second loop, it has to go through the third one, and again it has to give all 12 volts that it is carrying to that resistor, and so the value of V3 is also going to be 12 volts. As a kind of shortcut, you can of course remember that in a parallel circuit, the voltage across each loop is going to be equal to the voltage of the battery or the cell in the circuit. Now let's consider the current then. So we start off with having 12 amps of current. Now current splits up when it gets to a junction, so some of the current will go straight on and some of it is going to turn and go down this branch. Now sometimes it splits up evenly and sometimes it doesn't. So we need to work out how much current goes along here, and if we know that the potential difference is 12 volts and the resistance is 2, we can actually use an equation to work out the current. We know that potential difference is current times resistance, so the current will be the potential difference divided by the resistance, which is 12 divided by 2, giving us 6 amps of current flowing through this branch. Now, if 6 amps of current has gone through there, that means that 6 amps must carry on here. Now it then splits up again at this junction, and we'll do the exact same process to work out how much current goes this way. The potential difference is 12 volts, but the resistance this time is 4 ohms. 12 divided by 4 gives us 3 amps of current going this way. Now finally then, we need to work out the current going here, but we can't use V equals IR this time because we don't know what the value of the resistor is. We do know though that 6 amps entered this junction and 3 amps of it went that way. So if 6 was coming in and 3 went this way, then the other 3 amps must carry on, meaning that A3 is also 3 amps. We can then work out the value of the resistor R. To work out the value of the resistor R, we use V equals I times R again, but this time we do potential difference divided by current, which gives us an answer of 4 ohms. So back onto today's lesson then. Today's success criteria is to know mains electricity is at 230 volts and 50 hertz. We're going to describe the difference between alternating current and direct current, or alternating potential difference and direct potential difference, and finally we're going to explain how earthing works. So, definition of direct potential difference then. This is essentially what we get out of batteries. Now, direct potential difference always acts in the same direction. That basically means that the current will only flow one way around the circuit. By contrast, when you plug something into the mains electricity, you get out an alternating potential difference. Now, an alternating potential difference is one that reverses its direction periodically. Mains electricity actually reverses direction 50 times per second. So mains electricity in the United Kingdom is supplied at 230 volts and it has a frequency of 50 Hz. A frequency of 50 Hz, like I've mentioned, just means that it changes direction 50 times per second. Now we can look at what a graph of potential difference looks like. The graph here on the left will be for an alternating potential difference because, as you can see, the potential difference on this trace goes negative and then positive, negative and then positive periodically. However, for the one on the right hand side, the potential difference doesn't change. It is a straight line, which means that that will be for a direct potential difference. Right, now let's look at the structure of a plug then. As you can see on the diagram, we've got the structure of a plug there, and we've got a live wire, an earth wire, and a neutral wire. Please note that the live wire is brown in colour, the earth wire is green and yellow stripes, and the neutral wire is blue in colour. Now the earth wire connects to the ground in your homes so that you are always earthed. As I've just said, it's green and yellow stripes and it is always at 0 volts. The live wire carries a high voltage current, usually 230 volts in the United Kingdom, and it's brown in colour. The neutral wire is lower voltage, usually around 0 volts, and its job is to complete the circuit, because remember, a current can only flow if we have a complete circuit. So you could think of the neutral wire as carrying the electricity back out of your houses after it's delivered its potential difference. Now the job of the fuse is to break the circuit if too large a current flows through the live wire. If the current was too large, that could be dangerous because it could damage appliances like your mobile phones, which have got small sensitive circuits. It could also potentially cause a fire as well, so fuses are a very important safety device. The fuse is always connected in series with the live wire and the live pin. Now you might notice as well, if you've ever looked at a plug closely, that one of the pins is longer than the other two, and it's the one that is in the centre, and you can see from the diagram that that is the one that connects to the earth wire. So the earth pin is longer than the other two pins on the plug, and that is so that you are always earthed before a current flows. Now please remember this, it is never safe to touch a live wire even when there is no current flowing. That is because your body is at 0 volts and the live wire is high voltage, usually 230 volts. So if you touch the live wire, because that is 230 volts and you are 0 volts, there is a big potential difference between you and the live wire, and that will cause a current to flow from the live wire to your body, and that is what an electric shock is. Now let's just look at the materials that we use to make a plug. The inside of the wiring of the plug is actually made out of copper. The reason we use copper is because it's a good conductor of electricity, but importantly as well, it is able to be bent easily. Now, because it can be bent easily, that means the wires can be put into any shape that we need them to without them breaking, which is obviously a very good thing. The pins, though, we don't want to bend easily, and so therefore we make them out of brass. Brass is used because it's a good conductor and it is hard. It also doesn't rust or oxidise very easily. And then finally, plastic is used for insulation around the wires because it is a good electrical insulator. Now let's talk about how this idea of earthing works then. What I've got for you here is a quick talk through about how a toaster should work. Now what you can see from this diagram is that the current will enter the toaster through the brown wire, which is the live wire. It then travels through the heating element of the toaster and then back out through the blue wire, which is the neutral wire. If I use the laser here, you can see, follow the laser through. The current comes in through the brown live wire, it goes through the heating element of the toaster and back out through the neutral wire. And that is when the toaster is working properly. Now, when the toaster is working properly, the earth wire has no job whatsoever. However, an issue can happen if a fault occurs in the toaster, which means that the live wire then ends up touching the case of the toaster. Now the case of the toaster is made out of metal, which is a conductor of electricity, so the current will come through the live wire, and then instead of going through the heater of the toaster, it then goes onto the metal case, so we then have a current flowing around the metal case. That is very dangerous because if you come along and then touch it, you will get an electric shock. Now that electric shock at best might give you quite a surprise and a jump, or at worst it could cause serious injury. The earth wire prevents you from getting an electric shock if this happens, and I will show you why now. The earth wire is connected directly to the metal case. It isn't part of the circuit with the live and neutral wire, it just attaches to the metal case. That means that when the current comes in through the live wire, if for whatever fault has occurred the current goes onto the metal case, the current will then immediately go back through the earth wire and away, so that if you touch it, the current chooses to go through the earth wire instead of through you. Now, what will happen is the fuse is actually going to melt if this happens, because the resistance of the earth wire is very, very low and the resistance of the metal case is very low. There will be a surge in the current which will cause the fuse to melt. And that is how the earth wire prevents us from getting an electric shock. Okay, I've got a task for you to do here considering electrical safety. A man is using an extension lead so that he can use an electric drill outside. Now I've given you there a diagram of the electric drill and a diagram of the extension lead. I want you to write down an answer please to what the man should do to the extension lead before beginning to use the drill. Now there's 3 marking points to this. Have a go, see if you can get all 3 and check your answer in a moment. Okay, so in order to use the drill safely, he should completely unwind the extension lead. Now I do appreciate that you might think, well, that's dangerous because what if you trip over it, if you've got more extension lead out than what you would normally need, but it's actually the approved way of using an extension lead, because if you don't completely unwind the extension lead, the wire will overheat because the wire will get hot anyway, and if the extension lead isn't unwound, then all of the wires, because they are touching each other, they will all make each other get hotter, and so the wire will overheat, which could cause an electrical fire. Okay, let's have a go at a target board activity now. I've put on the board for you there 10 different words: green, brass, tin, frequency copper, alternating, direct, batteries, 0 volts and your body. What I would like you to do please is to write some sentences, write a list of sentences that use these words, and I want you to see how many sentences you need to be able to use all of those words. If you wish, you can use the words more than once, and of course you can use other scientific words as well, but let's see how many sentences you can get down, and let's see if you can get them in fewer than me. So my effort at this was to produce these sentences. I've got 4 there, as you can see. The earth wire is yellow and green, so I've got the word green in, and it is at 0 volts, that's the second one, like your body. 3. I'm quite pleased with that one, to get 3 keywords into one sentence. My second one was that the PD of the UK main supply is alternating, there's the 4th word, and a frequency, 5th word, of 50 Hz. Then I've said that the pins of the plug are made out of brass, that's my 6th word. The wire is made out of copper, which is the 7th, and the fuse is made out of tin, which is the 8th. And then I get the final 2 words in my last sentence, the 4th sentence: batteries are a source of direct potential difference. Okay, I'm now going to give you some time to have a go at some questions from a worksheet. Obviously you can read through the questions and then we will mark the work in a second. So, now that you've had a go at those questions then, let's see what the answers are. So the first one, the warm-up one, is just a gap fill exercise. It says the live wire is, and the answer to that is brown, and it is a potential difference of 230 volts. The earth wire, on the other hand, is green and yellow, and is at a potential difference of 0 volts. Now question 1. A toaster is connected to the mains electricity supply using a 3-core cable. State the frequency and potential difference of the UK main supply. So the frequency is 50 Hz and the potential difference is 230 volts. 1.2. The toaster cable has a fault such that the live wire is in electrical contact with the neutral wire. Explain why the toaster will not work while this fault remains. Well, let's think about what actually goes on then in the toaster. So the current enters the toaster through the live wire, and it should then flow through the heater inside the toaster, and then the neutral wire should complete the circuit. Now, if the fault means that the live wire is touching the neutral wire, then that means that the current will pass straight from the live wire to the neutral wire without actually going through the toaster, and so therefore the toaster will not work. Question 2. The cable that connects an iron to the main supply has become worn with use. There is no insulation covering part of the live wire. The iron is plugged in but switched off. 2.1. State two purposes of the insulation that covers the live wire. Well, it's so that it can be easily identified by its colour as being the live wire, and it is also to prevent an electric shock because the insulation obviously prevents an electric current from flowing out of the wire. 2.2. A man switches on the iron and touches the exposed live wire. He receives an electric shock. With reference to the electrical potential of the man, explain why he receives an electric shock. So it's all due to the fact, of course, that the live wire is at 230 volts, whereas the man is at 0 volts. So there is a large potential difference between the wire and the man, meaning that a current is going to flow from the wire to the man. 2.3. The socket is switched off and the iron is unplugged. Explain whether there is still a danger of the man receiving an electric shock from the plug socket. The short answer to that is yes, there is, but let's expand on that because it's 3 marks. Even though there's no current flowing, there is still a potential difference of 230 volts, and so if the man touches the wire, a current could still flow through the man, giving him an electric shock.